Hello everyone. Today's topic of lecture is going to be on radiation physics. It is important for us to understand how X-rays are produced, for us to gain a better understanding and to approach it in its application in various forms of uh, radiation techniques that we use, be it intraoral radiography, extraoral radiography, or specialized radiographies such as computed tomography, or also even be it to the extent of radiation therapy. So, production of ionizing radiation such as X-rays, understanding the nature of it becomes quite essential. So to start off with, we all know that Dr. Wilhelm Conrad Röntgen is the father of radiology. There are a lot of controversies, just like how we have something between Edison and Tesla, because the entire production of X-rays was based on the uh, discovery or invention of a vacuum tube. Basically, we all know that in the component we have a vacuum tube within which these X-rays are produced, and in our case, especially the Coolidge tube. So there are a little bit of back and forth, but it's a renowned it's a renowned fact that Dr. William Conrad Röntgen is the father of radiology, and the image you see there is the first ever radiograph of a human being that was taken, and this actually belongs to that of his wife. And If we just go back to history and try to find out how he found out about the X-rays, existence of X-rays, and how to effectively use it in medical imaging. It's a very interesting story by itself. So we'll keep that story aside and we'll just stick to the physics in today's class. And moving on, the ionizing radiation part. For everything, there is a basic structure component, and we all know that atoms are the basic units of matter and define the structure of elements. So, atom comes from a Greek word which means indivisible. So, and we all know that it's taught in school. We all know that atom has a central nucleus and it has electrons revolving around it, and the central nucleus consists of protons and neutrons. Whereas protons have a positive charge and neutrons have no charge, uh, and the electrons revolve around the nucleus in orbits. So the orbits are defined as in various alphabets, the first and foremost orbit you have is the K shell, then the L shell, M shell, and N shell, and each shell or each orbit has a capacity to hold a certain number of electrons. Now, understanding this, we have already studied this in our schools, and this is taught in these days. It is taught very early in school, and we all know that this is the basic component, but understanding this basic component is very essential because the two typical the two major the characteristic radiation and Brahma-Armstrong radiation that we study about the production of X-rays uh, is, uh, is mainly focused on the arrangement or the structure of an atom. You need to understand the structure of an atom for you to understand Brahma-Armstrong and characteristic radiation, which we will be seeing further. So what we have to remember here is that there is a central nucleus which consists of protons and neutrons, and there are electrons revolving around it in shells, and each shell has a capacity to hold a certain number of electrons within it. For example, the K shell can hold 1 electron, the L shell can hold 2, and M shell can hold 3, and N shell can hold 4. And depending upon the size of an atom, the shells might be more or less depending on. And when you reduce the number of electrons revolving around it, that is where the atom becomes kind of unstable. So atomic number is a quantity that generally denotes the number of protons, and the number of protons and neutrons combined together generally denotes the mass number. Saw a little bit about proton and neutron, and we said that this electron keeps revolving around the nucleus. And how does that happen? So there exists an electrostatic force, that is, there is an attraction. At the same time there is also a kind of a repulsion. There is both attraction and repulsion that enables to levitate the electrons and keep it revolving around the orbit. And this ability of the the central nuclei to hold these electrons in its orbit is called as binding energy. So it requires a certain amount of energy. So it requires a certain amount of energy to pull and to push. So it is doing both at the same time. So the more closer the electron is, the binding energy is going to be more, and the more further it is, the binding energy is going to be less. Why we are talking about all this, you will understand when we go about it in characteristic and Brunham strong radiation. And then moving on to ionization, it's a process of converting atom into ions. Uh, by theory and definition, it's a process by which electrically neutral atoms or molecules are converted into electrically charged atoms and molecules. It is one of the principal ways radiation, such as charged particles and X-rays, transfers its energy to matter. So how that happens? For that we have various theories that come along with its way. So its ability to change the form, the ability of a radiation or an energy to convert an object into something different. The principle of ionization, the basic of its biological effects, will be studying further in radiation biology, but it is more focused on water. How water is converted into hydrogen peroxide, H2O is converted to H2O2 with the influence of ionization, is what we'll be studying in detail in radiation biology. But for now, just know that ionization is the process by which electrically neutral atoms or molecules are converted to an electrically charged atoms or molecules. So, ionization radiation is capable of producing ions by adding an electron to an atom, and it has two types, which is particulate radiation, and you also have electromagnetic radiation. So, particulate radiation basically consists of particles that have mass and energy, and may or may not have an electric charge. The difference itself can be understood with the protons and electrons and beta particles and alpha particles, where you have the positively charged alpha particles, the negatively charged beta particles, and there is no charge when neutrons. And examples of particulate radiations are alpha particles, protons, beta particles, and neutrons. And the it can either be an ionizing or non-ionizing radiation, depending on the energy or ability to penetrate when it comes to particulate radiation. Moving on to electromagnetic radiation. In the later half of 19th century, a physicist named James Maxwell put forth a theory called electromagnetic theory, where he said that the electric field and magnetic field alternatively travel in a wavy pattern, just like the basis of alternating current, and they exist in a wide range of spectrum, giving rise to various particles. In his theory, explained that electromagnetic radiation is similar. It has no mass, carries energy in waves and electric and magnetic disturbances, and it might be defined as an electric and magnetic disturbance traveling through space at the speed of light. So the electromagnetic spectrum is in a way of ordering a group of different electromagnetic radiation, and all the members of the electromagnetic spectrum have the same velocity as of the of a speed of light, and vary only in their energy, wavelength, and frequency. So the first line that you see that penetrates Earth's atmosphere, it says yes, Y stands for yes, and N stands for no. And in the second, you can see, in the second row, you can see a red colored line, which kind of shows, the wavy pattern. So the more wavy it is, the more alternating it is, the more energy it has. The less wavy it is, the less energy it has. So you can understand by this that radio waves, which we commonly use in our AM FM radio, we use for a and for our walkie-talkies, and all these radio waves, they consist of very low ability, penetrating ability. So they are generally present, but their effect on humans and their effect on you know on any living organism is very quite minimal. And their ability is to travel large distances, so hence we are able to use it in communications. Moving on to microwave, where it increases, but it has a very limited capability, it cannot go beyond a certain period. Moving on to infrared, visible, ultraviolet which we get from our sun rays, which they have, due to its increased level of the penetrating ability and its frequency. We understand that UV rays at some point, when unfiltered UV rays can even give rays to can cause molecular structural changes which might lead to cancer. And moving on to X-rays, more higher wavelength, and moving on to gamma rays, even more higher, so which is used effectively in radiation therapy. And this is a chart that you will very commonly come across, even if you Google it, or if you come across any textbook for that matter. It's a chart that you will very effectively come across, which explains various components of electromagnetic spectrum, and their properties, their capacity to make any changes, and their ability to generate a temperature, that is increase heat or decrease, and their effect on biological molecules are all explained in this chart. This is what I explained before. The more wavy it is, the more penetrability it has. So as we all know, the sequence goes: the least penetrable is radio, followed by the ones which we generate for TV and this thing. Visible light has a certain amount of penetrability. Moving on to X-rays, we all know that it cuts through soft tissue, and it can be only stopped by very hard tissue. Moving on to gamma, which can even sometimes cut through, and this thing. And cosmic rays, which does tend to have, and that cosmic rays effect in our this thing is, in our case, is filtered by the ozone layer which we are protected. That is why when you take a flight, you tend to get exposed more to cosmic radiation. So in your flight ticket, if you pre-book a ticket, a detailed itinerary of your ticket, they'll show you how much of radiation you are exposed to by taking that particular flight journey. So the more higher you go, more closer you go to the climb up the atmosphere, the more radiation you get. The more closer to Earth, the less you are. So this is as far as electromagnetic spectrum goes. In our topic, X-rays, it falls under the spectrum. We understand that there is particulate and electromagnetic. Here we are concentrating on electromagnetic. Moving on to energy, like I mentioned before, it is the ability to penetrate. The shorter the wavelength, the higher the energy, and higher the frequency, and also higher the so X-rays, they are electromagnetic radiations. They are defined as weightless packages of pure energy photons that are without electric charge and travel in waves along a straight line with a specific frequency and speed. So the properties of X-rays are that it belongs to the family of electromagnetic radiation, and the wavelength is between 10 Armstrong and 0.101 Armstrong, and travel as the same speed of that of visible light, and it travels in a straight line. It is invisible, it cannot be visualized, and it cannot be neither reflected or deflected by electric or magnetic field. Even though we describe electromagnetic radiation as an alternating electric and magnetic field, X-rays property is such that it cannot be deflected with electric and magnetic field. It has the capability of ionization due to its increased energy and penetrability. It is used in radiation therapy, and it is also used in imaging studies, and because of its increased energy and strength, in maybe lower doses of X-rays might not be that much of a big biological, might not make that much of a biological changes in humans, but if you take microorganisms into account, X-rays can be used to kill them off. It can be germicidal, that is bactericidal, and can be used and is used in some cases for sterilization also, because it's a very expensive way of sterilizing something. We effectively use UV radiation, UV rays for sterilization. You would have come across that in barber shops. In nowadays they sell, after this corona thing, they're selling hand some pocket UV sterilizer for you to put your mobile phones and masks and everything. So UV rays at certain to a certain degree of time and exposure has the ability to cut off or become germicidal. Same goes for X-rays and gamma rays too, and it can cause its long-term exposure of shorter or longer wavelength of X-rays can cause biological effects and can affect a photo. So the uses of X-rays are such that it is used in dentistry, medicine, to diagnose a pathological, that is radiography, and radiation therapy. So radiography is different, radiation therapy is different. Radiography is used for diagnosis. So we use it for imaging studies. It's called imaging studies, where we take plain film radiography, we take specialized radiography, we take scans, CT, CBCT, PET scan, all this where we use ionizing radiation. And whereas radiotherapy is where we use the same more potent form of X-rays to cause biological changes, that is to deteriorate a tumor mass or a carcinoma. And used in sterilization and in a detective department, we would very commonly come across X-ray scanners in airports to scan luggages, and in industries, especially they use this in steel industries to detect micro cracks within steel, metal or steel plates, and industrial grade of X-rays to test the quality of paintings, to detect defects in tennis balls, tires, and various other materials, and to detect cracks in body of airplanes. So this is the typical intraoral machine that we use. The machine generally consists of a tube head, consists of a control panel, and consists of a support arms. So it is supplied in two forms. One is a wall mount. What you see in the picture is a wall mount, where the entire machine is fixed to a wall. So it has a limited capability. That is, it can only be used within a certain area. It cannot go beyond that. And what you will see in our college is a mobile unit, which has a stand. Apart from the supporting arms, it will also have a stand, vertical stand, and it will have wheels which you can mobilize. You can take it to various this thing, and it can be used in multiple cubicles at the same time. So this is a wall mount unit, and the control panel generally consists of all the measurements. Previously, we used to have everything used to be very manual, everything had to be manually keyed in or adjusted. But nowadays, it has toned down, and the manufacturers have made it is in such a way that we get preset or preloaded settings. We just have to choose the tooth and the site of exposure, and the machine will adjust itself accordingly. And the components of the tube head will go as we see further. And the supporting arm is generally hydraulic. We have to understand this tube head, although it looks smaller in size, it looks easy, but in reality it is so heavy because it is a lead container with insulating oil and a lot of components within it. It's a very heavy object, which cannot be handled by itself. Although we have a portable IOPA machine, it is not very easy to handle it and take X-rays. Hence, we have this hydraulic. So the control panel generally consists of an on-off switch, an indicator light, an exposure button, and control devices for time, kVp, and milliamperage. In recent times, machines you don't get the ability to alter kVp and milliamperage. You only have a control device for time, and we all know that apart from this thing, you have to arm the machine in the control panel, and you will have a trigger switch outside. Once you press the trigger switch only, X-rays will be produced and the patient will be exposed to. So you have to arm it and then shoot. This is to prevent any accidental exposure to. So moving on to tube bed, another important, the most important component here. So like I told you before, it has a very tightly sealed heavy metal housing, and it is generally coated with lead as to prevent any scattering of X-rays and to converge it into one point. And it has insulating oil it also acts as a coolant, which is which cools down the, because a lot of heat is generated in production of X-rays, because this entire component, the tube bed, also consists of a step up and step down transformer, so a lot of heat generation will be there. The insulating oil, it is also a very good suspension medium. At the same time, it also acts as a dissipate heat to some extent. The X-ray tube, which is a vacuum tube, or what we call a Coolidge tube, which consists of the anode and cathode within. Aluminum discs, lead collimators, aluminum discs which uses filters, lead collimators, and position indicating device. These are part. And the components of X-ray tube, so devoid of everything else, what lies within the tube, we have your negative cathode, the positive anode, and the lead glass housing within which it is kept in. The tube is kept vacuum because presence of any air particles will influence the production of X-rays. Okay, moving on to, we'll see these each components a little bit individually for us to better understand the production of X-rays. So the cathode is negative charge, and it is made up of a tungsten wire. It is which is 2 millimeter in diameter and 1 centimeter in length, and it is mounted on two stiff wires that can carry power supply, and it is mounted in a cup shape holder which is made of molybdenum. And so here it's a picture depicting how cross-sectional view as to how the cathode is positioned within the molybdenum cup. So various sections, the cross section and the lateral section of the images, how it is. And then moving on to the anode, an important component. It has a positive charge electrode, and again it is again made of tungsten, where here it is embedded within a solid copper rod. There it was molybdenum, here it is solid copper rod, and tungsten serves as the focal spot, and it converts the bombarding electrons to X-ray photons. So the necessity for the tungsten to be embedded within copper is to dissipate heat away from tungsten. So again in anodes we have two components, where one we have a stationary anode and then we have a rotating anode. So a stationary anode is a single block of copper stem within which there is a target area which is made up of tungsten, and it is stationary, and the cathode which produces electrons directly goes and hits into the anode, and then it is once X-rays are produced, it is diverted. The problem with this is there is too much of heat generation. Even though we have copper stem to try and dissipate the heat as much as possible, the wear and tear of the tungsten becomes more, which eventually leads to pitting of the tungsten material in the this thing, thus affecting the quality of X-rays produced. So so this is the kind of anode that is actually used in intraoral machines. The reason for it is because the amount of the X-rays or the quality of electrons that we produce is of very low very a very low power that will not cause that much damage, and hence we use this higher amount of this thing. We have something called as a rotating anode, where once you expose it, it goes into a full rotation until it cools down and comes back. We'll see that as we go further. So the production of X-rays falls under the principle of thermionic emission, where when we pass electric current through that tungsten filament, the tungsten wire, the cathode we talked about, what happens is that once it starts heating up, it will start emitting electrons, and this electrons goes and hits the target anode. So here, if you notice something, we'll be using tungsten in both cathode and anode. Why? Because it's an ideal target when it comes to anode, and it has a very high atomic number, which means it has a high melting point, and it has high thermal conductivity, and it has low vapor pressure. That is, see, any material, when you subject it to heat, constant heat, it has the tendency to vapor off. Okay, here, because it is within especially within a vacuum tube, the vapor will again interfere. So here we need something that has a very high very low vapor pressure and very high melting point, so that it does not give up that easily. So the high atomic number is best suited for most efficient production of X-rays. The high heat generated in anode is relevant to the high melting point, and high thermal conductivity dissipates the heat to the copper stem, and low vapor pressure helps to maintain the vacuum. And then moving on to the focal spot in the anode. The focal spot is generally sharp. It is the area where it shoots. So you can compare this focal spot to that of your the focal spot that you have in your eyes, that is the rods and cones in the retinal layer. The smaller the focal spot is, the sharper the image. If your focal spot is disturbed and it is distributed, you are going to get blurriness of image. So the focal spot is kept as sharp and small as possible. And to take advantage of the focal spot, like I told you before, that X-rays can neither be attracted nor deflected. So the only way how we are going to angle the beam is by angling the entire the apparatus. So we take advantage and of that focal spot, and we have given an angulation of 20 degree, so that we direct the beam that is produced through the So another method of heat dissipation is done by rotating anode. I told you this before, and this rotating anode is generally used in panoramic radiography and other higher forms of machinery, CT and CBCTs. So the rotating anode is nothing but, instead of a single copper stem block, it is a copper disc within which a layer of tungsten is embedded, and this disc keeps rotating. Once one shot of that is one exposure, one load of exposure is given, it goes for a rotation, one full rotation, during which it cools down. And this they have further developed into various other processes also, but at this point, how it functions. So when an electron beam strikes the target in that particular area, once the target is achieved, it goes for a rotation halfway, which it cools down and comes back to becoming cold, ready for the next exposure. So the lead has a lead glass housing, the lead glass vacuum tube that prevents X-rays to escape in all directions. The central area has a window which directs the X-ray beam, aluminum disc, collimator and position indicating device. Why it is evacuated? Because we need to prevent collision of electrons with air. Because electrons have the ability to interact with gaseous molecules. Here, what we want our electron to interact with is the atoms in the anode, not with anything else, and to prevent oxidation and filament burnout. So for it's basic simple physics, that if you want to burn something, you need oxygen. For fire to burn, you need oxygen. You cut off oxygen, it's not going to burn. There is nothing to burn. So that principle is applied here, so that the filament does not burn out. If I do not know how many of you have come across this, but in older days, even now these bulbs are available, these yellow colored bulbs, where you can see a string of light. Nowadays it's used for decorative purpose, but maybe some 30-40 years before it was present at every household, like yellow bulbs. If you see in the middle of that bulb, you will see like three pins in which there will be a very thin filament hanging around. That is essentially made of tungsten, which burns. And again, that is made of vacuum so that it doesn't burn out. It is going to be so thin, and that small filament, because we need longevity for that machine. You're going to invest a lot of money. We need to take a lot of images using that machine. If the filament burns out, then it's not like just changing a bulb. You just simply don't remove it. You have to remove the entire vacuum coolage tube, and you have to replace it. It doesn't just one component gone and off. So it doesn't work like that. So it is important that we avoid the burnout as much as possible. That is why we get rid of all the gas vacuum. And moving on to the power supply, here, like I told you, the power that is sent through the cathode and this thing, it is necessary for the X-ray tube to function, because we need to produce that thermionic emission, to increase the heat through this thing to produce electrons, to heat the filament to generate electrons, and to establish high voltage potential between anode and cathode to accelerate these electrons to, because it has to go all the way from cathode to the anode, and it has to strike the anode enough that it is able to, produce. And tube current is generally the amount of electricity. So here we have two basic uh, you know values that we will very commonly come across in your when you talk about the tube current and voltage, where we have MA, milliampere, and kilovoltage, kVp. So here the step down transformer reduces the voltage of incoming alternating current to 10 volts. We all know that our socket consists of 220 volts, and there is a step down and step up transformer which moderates this incoming current, making it suitable for our need, and regulated by the filament control MA switch, and this in turn regulates the temperature of the filament, thus the number of electrons emitted. So the MA, the amount of current that you are passing through the filament, is directly proportional to the number of electrons that is emitted from the this thing. So thus, by altering the current, I told you that nowadays, these days, we do not have the malleability to do that in our intraoral machines. But even today, in our extraoral machines, if you see in our OPG machine, you can see the option of altering the kVp and MA. So by doing that, what you are trying to achieve is that you are increasing the production of electrons, thus more production of more X-rays, that is more intensity, more X-ray. And tube voltage. High voltage is required between anode and cathode to generate X-rays, because the electron has to travel all the way from cathode and it has to strike. It is not like it is going to go and it is playing what ice boy or something. It's just touching and running away or something. It has to strike the anode. So that kind of drive has to be given. For that, high voltage is required. And auto transformer converts the primary voltage from input source to secondary voltage. So the kVp dial selector generally converts the incoming line current as high as 60 to 100 kVp, boosting the energy of electrons. Okay, so MA decides how much electron is produced, and KVP generally decides what is going to be the energy of the electrons, that is how intense it is going to be. Because the current that we use here is not direct current, what we use here is alternating current. So going back to your school physics, we know that there are two types of current. There is DC and there is AC. DC generally refers to the power that you generate from your batteries, right? Your the cell, the AAA, AA, or your iron cell, carbon cell, or everything. That is direct current. and AC is alternating current, which you get from the power socket, right? Alternating current, like you remember, if you remember from your school theory, it occurs in a wavy pattern. It has up, it crests and then it plummets, crests and plummets, crests and plummets. Here in this alternating current, we only need one half of the alternate to produce uh, X-rays. The other half is not actually utilized. Previously, there is something called as duty cycle, which we will see further. Previously, when we had a very not so sophisticated or very basic form of transformers, it would take a lot of time to produce that kind of X-rays. A lot of time and a lot of electricity and energy to produce. But nowadays we have an automated auto transformers, which cuts off and gives us the only the necessary parts and minuses of which is not required in alternating current. So hence, because the line voltage is variable, the voltage potential between anode and cathode also varies. Hence, varies. Here the important component for us is going to be the KVP. KEV is just theory, and KVP and milliampere MA is what we'll be actually handling during our while taking X-rays. And during the other half of the cycle in alternating current, the polarity reverses, and for example, if cathode is positive, then it becomes negative, and anode is negative, it becomes positive. That is, it totally reverses. This is called inverse voltage and reverse bias, and this is rectified by auto transformers. We do not have to go much into it because we have already advanced, and we have auto transformers fitted in almost everything. Nowadays you get these auto transformers even in small electronic components, so it's not much of a significance. And tube rating, each machine comes with a tube rating specification. It is the maximum exposure type the tube can be energized without risk of damage to the target. So tube rating means it is basically the structure of the tube. So if for example, if you see the tube of an OPG machine or a CBCT machine, it is obviously going to be different than that of an intraoral machine. So the capacity of the tube generally gives us the idea for how much can be produced. So I mentioned to you before regarding duty cycle, like where I talked to you about alternating current, where we use only one component of the alternating current to produce the the necessary electrons and the kind of intensity of electrons that we need. The other half is actually not required. So this kind of puts a restriction over our you know the ability to produce constant bursts of X-rays. So it's not like just how we record a video or can click continuous snaps with our mobile phone. So this exposure in our intraoral machine, especially with the stationary anode, there is going to be a significant amount of time. Now manufacturers have come up with a lot of advancements where the duty cycle time has reduced very significantly, but still it does exist. So you cannot right away continuously keep exposing, like keep shooting X-rays. There needs a significant break between one burst of exposure and another burst, and this is the frequency with which successive duty cycle. So we understand what are the components of the X-ray tube, and how X-rays, how we generate these electrons. Now we have to understand how these electrons interact with the atoms in the anode. The electrons from the cathode interact with the atoms in the anode. So that comes under various topics. We have coherent scattering, photoelectric absorption, Compton scattering, differential absorption, secondary electrons, and beam attenuation. So we'll see them one by one. To start off with coherent scattering, and coherent scattering, it is also known as Thomson scattering. So in many of your the textbooks that comes out of UK, you will see this mentioned as Thomson scattering. So do not get confused. Coherent scattering and Thomson scattering is more or less the same. It occurs when low energy incident photon passes through the outer electron of an atom, which has the least binding energy. And this incident photon interacts with the electron of the outer shell by causing it to vibrate momentarily at the same frequency as the incoming photon. And the incident photon then ceases to exist, and the vibration that is caused in the electron radiate in energy in the form of another X-ray photon with the same frequency and energy in the incident photon. So essentially what happens when it comes to coherent scattering or Thomson scattering is that here uh, I told you that there is a binding energy. So the more closer the shell is, the more binding energy, and more the further is the lower binding energy. So this photon from the goes and it kind of disturbs the electrons in the outermost shell of an atom in the anode. Thus, this vibration that is, or the disturbance that is caused by this photon leads to emission of certain amount of X-rays. But this coherent scattering is not something that is very is not something that we need for making a radiographic image. In fact, this is a very low energy photon which directly leads to film fog. It does not actually create an image, rather than creating an image, it actually causes an artifact. So up to 7% of coherent scattering can occur while our aim is to, from cathode, to produce a certain number of electrons with a certain intensity or with a certain power, right? What happens in is that while, let us say, 83% or 80%, 90% we are able to achieve, there is this remaining you know some 15 10 to 15% of electrons which are not going to be, or energy that are not going to be that are not going to give us desirable effects, that are not going to be of that good energy that we are aiming to produce. So one of them is coherent scattering, and it generally causes film, and this is the one which we tend to filter out. This is why we use filtering device to filter out all these low energy photons. Then we have photoelectric absorption. So photoelectric absorption, it generally occurs when an incident photon collides with an inertial electron in an atom of the absorbing medium. And this electron is ejected from the shell, resulting in ionization, and becomes a becomes a photoelectron. And the kinetic energy imparted to recoil the electron is equal to that of the energy that is overcome the binding energy of the electron. In this particular case of photoelectric absorption, the low atomic numbers, that is in most biologic energy of incident photon, it mostly occurs in the K shell because the density of the electron cloud is greater in that particular region, and its interaction exists. About 30% of photon absorbed from this dental X-ray beam are absorbed by the photoelectric process. This is another process um, where the where a particular electron enters into an atom, and it displaces a particular you know an electron from a particular orbit, and the energy that is needed to compensate that. So what happens when let us say, for example, shell number 1 2 3 4 we saw, right, KLMN. So in that, let us say it has displaced an electron from the K shell. Okay, so the atom becomes unstable. So immediately the atom, what it does is, to stabilize itself, it borrows another electron from the outermost shell, and it keeps jumping, compensating. So this kind of transition, this kinds of transition of the electrons from this thing uh, enables in release of ionizing radiation, and photoelectric absorption generally accounts for 23% of produced. Filtration, we talked about filtration prior. It is to limit the X-rays only to the useful energies. We do not want low energy photon or energy pockets which causes artifacts in our films. We want only a desirable amount of energy electrons to produce an image. So to filter out all these low intensity or unwanted low intensity X-rays, we use something called as a filter. And the filtration material is generally aluminum. And X-ray, to comprehensively tell, the aluminum preferentially removes many of the low energy photons with lesser effect of higher energy photons that are able to penetrate to the film. And determination of the amount of filtration required for a particular X-ray machine, KVP and inherent filtration of the tube and its housing must be considered, because we already told that it is housed in a metal. It is housed in a metal container with insulation with oil. And these materials can include the glass wall of the X-ray tube and the insulating oil that surrounds the dental tubes and the barrier material that prevents oil from escaping through to the X-ray port. So the total filtration is almost equivalent to the inherent filtration plus external filtration, that is the aluminum disc which we are going to use. So the filtration is not just brought about by the aluminum discs alone. It also involves the inherent filtration that is provided by the glass and the metal housing and the barrier materials. Moving on to dosimetry. So dosimetry is the quantity of radiation exposure, or the dose, and the term dose is used to describe the amount of energy absorbed per unit mass at the site of interest. So exposure is a measure of radiation based on its ability to produce ionization in air. So what we have to understand here is exposure is a measure of radiation based on its ability to ionize air under standard conditions of temperature and pressure. If air is not involved, it is still not called exposure. Only when air is involved, it's called exposure. So exposure is a measure of radiation quantity and in its capacity to ionize air, and it is generally measured in the unit Röntgen. The Röntgen applies only for X-rays and gamma rays. Moving on to absorbed dose, we have absorbed dose is a measure of energy absorbed by any type of ionizing radiation per unit mass or any type of matter. It does not just involve air or gas, it involves any matter for that matter. The SI unit of absorbed dose is gray, and 1 gray equals to 1 joule per kilogram. And the traditional unit, so the SI unit is gray and the traditional unit is rad, which stands for radiation absorbed dose. Okay, so 1 gray is equivalent to 100 rads. Okay, so SI unit is, so we have one international standardization standard SI unit, and we have a traditional unit for all of these components. So here the traditional unit is rad, and the SI unit is gray. So 1 gray is equivalent to 100 rads. Moving on to equivalent dose. The equivalent dose is used to compare the biologic effects of different types of radiation on tissue or organ. So when it comes to absorbed dose, it does not actually evaluate how much biological component is involved. That comes to equivalent dose. Equivalent dose generally designates the biological, the amount of radiation required for making biological changes in tissue or organ. And it is expressed in the sum to allow time possibility that tissue or organ has been exposed on more than one type of radiation. Therefore, for diagnostic X-ray examinations, it is generally equivalent dose. The unit of equivalent dose is sievert, which is denoted by an S SV sievert. So one sievert is equivalent to that of 1 gray. We know that gray is the SI unit of absorbed dose. So one sievert is equivalent to 1 gray. And the traditional unit for equivalent dose is REM, which is Röntgen equivalent man. And one sievert, that is one SI unit, one sievert is equivalent to 100 REMs, which is the traditional unit. Moving on to effective dose. The effective dose is used to estimate the risk in humans, how much risk of radiation can cause. And it is again measured in the form of sieverts, SV. Finally, radioactivity. The measurement of radioactivity describes the decay rate of sample of radioactive material. And the SI unit of radioactivity is becquerel, is given as becquerel. So the traditional unit for radioactivity is Curie, and the SI unit is becquerel, which corresponds to the activity of 1 gram of radium. So this is what has been given here, the traditional unit and the SI. So this is just a flow chart to whatever I told you before, how it flows, the absorbed dose to the equivalent dose to the effect. So again, going back to Compton scattering, which we have already discussed before, it results in almost all the scattering reaching film probability of occurrence. It directly with photon energy, independent of atom, 49%. I know at this point this is too much because there are a lot of physics that we have discussed. It might be a little boring, but please bear with me. We are yet to arrive at the important two components of production of X-rays. So to move on with Brill-Armstrong radiation, it is called the breaking radiation or general radiation. This is when X-rays are produced when high-speed electrons from filament are slowed down as they pass through or strike the nucleus of target atoms. So to produce X-rays, there are two types, two variations how we can produce. The one I already told you about. One is where we take a high intensity electron, it goes and displaces an electron that exists in another atom, which creates a certain amount of imbalance, right? And so the borrowing of the electron happens from the outer shells, other shells, and this leads to certain amount of kind of like production of X-rays. Whereas in Brill-Armstrong radiation, what they try, what it explains is that you do not actually have to displace an electron from another atom. Instead, what happens is that electron successfully enters through the orbit of the atom, and it gets deflected without having to displace any electrons from it. It just deflected. But what happens when this electron in the orbit is that it stays inside and it comes out. And the moment it goes inside and comes out, it kind of creates a certain level of instability within that atom, which leads to production of X-rays. That is the energy. It disturbs that binding energy between the nucleus and the electrons distributed through the shells. And this disturbance leads to production, where this passing electron, it goes in, because of the binding energy, it slows down and it creates a kind of like, it imbalances it a little bit, and then it exits out successfully without disturbing any of it. And this temporary state of instability brought about in this particular atom leads to production of X-rays. The necessity for understanding this theory is why we put forth various theories and why we try to study all of this is because how to effectively produce, because we told that if we are trying to produce let us say 100% 100 very good quality, very powerful for desired effect electrons, it is not going to be the 100 is not going to come out the same way. We can expect somewhere around 87% to 90% to come in these days, but there is still going to be a small margin of up to 10% which is going to be low incidence of photons. So understanding this mechanism helps us in a way to guarantee production of that particular quality. So we can minimize the number of low. So when it is it produce. Then moving on to characteristic radiation. Here X-rays have characteristic target material. So there is a difference between binding energies. This we solved already before. So the energy of the high-speed electrons that is produced by the cathode must be higher than that of the binding energy of the target electron. We are particularly targeting a electron in a particular shell. Okay, so for us to uh, displace an electron from K shell of an atom, from an electron produced from the cathode, the energy or the intensity of the power of the electron that is produced must be more powerful than the electron we are planning to or the binding energy of the electron that we are planning to displace. Only then it will be it is simple, like you should be strong enough if you want to push something out, right? Like if you try to push a small object, a table or something, you are able to push it because the energy that you push supersedes the stationary energy of that particular object. Whereas, let us say for example, it's a concrete wall or something which has for which you do not have that particular energy, you're going to fail. You're going to fail displacing it. Thus, you're not going to get a desirable amount of radiation from it. So the amount of radiation, so a high speed electron with at least 70 keV of energy needs to is required for you to overcome the binding energy of an electron in K shell. So electron enters, displaces an electron from the K shell, and both leaves. Now what happens is there is a vacancy created. So the atom is stable. During this entire period of instability, it only lasts for less than one hundredth or like maybe 1/10 or 100th of a second, for very short duration. In this very short duration, this imbalances produces X-ray electron. So what happens is during this time, to again become stable, what the atom automatically does is it borrows electrons from the outer shell. So from the outer shell to the inner shell. During this process, an X-ray with when you give 70 energy, 59 keV energy is produced from a K shell. So overall, if we have to talk about how it is produced, once you press the exposure button, electricity is passed, and it is passed through the MA switch, and electricity is sent through the step down and step up transformers, and it is sent to the filament to produce uh, um, you know electrons from the cathode filament, tungsten filament. On the other hand, electricity is also again produced and sent to the anode, KVP, which is the KVP, and sent through the auto transformer, and through the step of transformer is sent to the anode. Now there exists a certain amount of energy between them, so that the intensity of electrons is designated, and it goes, hits the target anode, and the Browne-Armstrong or characteristic radiation occurs there, and X-rays are produced, and it is sent out through the filter column. It is like kind of like what do you call, the size of the beam is designated, size and shape of the beam is designated by the collimator, and it is sent through the position indicating device. So this is a methodology of production of X-rays, radiation physics. I know this is little overwhelming, but don't worry, most of the components of what we saw in this lecture are basic radiation physics, which we would have studied in our high school. So don't confuse too much, and if there is any doubts, please feel free to ask. It's a very simple uh, theory, which is very once you understand it, it's going to be very clarifying, and I hope you all understood something from this lecture. So if there are any doubts, please do communicate, and we'll discuss it further. Stay safe. Thank you.